Our first talk and exercises today are going to be an introduction to statistics given by Maria. I just blasted out on the Slack a link to the IPython notebook that we'll be going through later, so eventually you'll want to either clone that or just download that IPython notebook and the corresponding data files that you're going to need. But first, I think Maria is going to have a brief talk on an introduction to statistics. So without further ado.
Okay, so actually the exercise will be a little bit mixed with the talk. So in the middle I will ask you to do something and to see on it, and then read from the lecture. So I will begin with the motivation, the need for statistics, why to learn statistics. And learning statistics, by this I would mean something like yesterday Adam talked about that it's better to have a very good, very deep knowledge about statistics. The problem comes, of course, with the size of the data sets we are dealing with, more on a regular basis than 10 or 20 years ago. For example, Gaia is up and working already, transmitting data. We have already done the processing, and we indeed did see that it means a quality difference when you have 3,000 or 10,000 data points, or you have billions of them. It's really a big. It makes a really big difference. So Gaia, the picture here in the background is. Oops. Go back. Okay. So every pixel's brightness is proportional to the number of sources that Gaia will see. You see the Magellanic Cloud, the plane of the galaxy, together with the dust, where you practically don't see anything, and the places where you see a lot. You have some idea about the globular clusters. One globular cluster, if you close up on it, looks like something like this, and of course this makes a huge database. Now, when you have, let's say, 10,000 objects, that's already a lot. You can learn a lot with 10,000 objects. But with 10 million objects, you will see the tails of the distributions. And that's completely different. There's no driving information in, say, 1,000 observations. What happens out there? It must be that with the statistical methods, how to extrapolate into these regions. Another problem is, of course, not just dealing with these data sets, how to in an automated way classify and give basic information every single little object here, but also how to find them in the databases. Again, you need extraction methods, very close, and you have to deal with data. Once you select it from this database, you have to deal with data together with contamination. These statistical methods are never so perfect as visual inspection. When you could look at the object, you could assess whether it's good for your planned research and or throw it away. No, you cannot do that. If you want to deal with huge databases, then you should be able to find the contamination also, so to deal with the contamination. And well, this is Gaia. Already with Gaia, the data sets are huge. There will be more than 1 billion objects in the final database, each with a time series of photometric and astrometric measurements. Some part of them also with spectroscopy. So it will make a database of more than 1 billion objects in the galaxy. And with LSST, this will be a little bit more appropriate illustration of that, what will happen. Another motivation why you should learn more statistics. While I was I have been working now since 6 years in astronomy, but before that I was a pure statistician during 8 years, just the first 2 years studying it and then doing a PhD in statistical methodology. And since then I could not get rid of a feeling that astronomers have a different view on the data, on the same data as a statistician. Astronomers see always the physical effect that they want to see. They are looking for the physical laws in the universe governing the behavior of the stars. You want to see something deterministic in your data. And for you, or for the general astronomer, this is what is essential in it. Anything else, noise, probabilistic structure, everything else is just annoyance, just nuisance, disturbance. You want to get rid of it as best as possible and as quickly as possible. Statistics have some somewhat different view. When you give a data set to a statistician, he or she will at once look at the probability structure of it. How the randomness is present in this data. What can be the distributional assumptions on it? How can you build up the statistical model for it? It's the first thing for the statistician is to model the noise, to find a good model for the noise, because the noise can really bias your estimation of the physical effect in the background. Especially if it's tiny, especially if it's mixed up with other physical effects, it's very hard to disentangle, and you have to know the probabilistic love to put a very good model both on the noise and the side and the other effect in your data. So the statistician's view is rather something like this. It's just a huge and hazy thing covering all your possible data, the space of all your possible data points, and this is what will drive the inclusion of this physical model. You have to learn to model this very well. And so finally, at the final stage, your task when you want to do research in astronomy with these big data sets is something like this huge big sea of randomness, of noise, of everything together that can influence your data set, and your objective is something like this. First you learn to navigate on this sea of random effects and noise, and try to find safely your way on it, and afterwards you can possibly catch your big whale, big white whale. Okay, so that's it. And therefore, what I would like to do is first is just try to put emphasis on the fact that you have to be able to identify the probabilistic model in your data. Then you have to find discrepancies with the supposed model, because every model is just approximate, so that I will try to give you tools to detect these discrepancies, to find out what happens, and then we will go to estimation, how to know better this model, how to get a first idea about it. I will deal only with the classical methods, because in the afternoon Jake will give you a good introduction into Bayesian statistics. But we will deal with a very simple way to have a first idea about the distribution. Then we will try to deal with some discrepancies in it, with outliers, what to do when you have outliers, and finally generalized from this method of moments, the likelihood inference, where you can include also already the physical laws in the parameters. And then I will say a few words about classical hypothesis testing and model selection. And at the end, I plan to have a go on a gnawed bone. It's already very well treated. It will be the period-luminosity relationship of the classical Cepheids, which sounds not very interesting, but you can observe how a simple linear regression can work, and how certain detection methods, certain tools that I tried to show during the lecture would give some idea about what can be the reason of sort of not working perfectly the model, and you will be able to find some limitations to the model. Okay, so that's the plan. Let's start with probabilities at the heart of everything. Probabilities usually can be introduced by a pure mathematical way. That's what I'm recalling here, by the axioms of Kolmogorov. So you have a space of possible elementary events. I did not write it because I did not want to over-complexify, but you have to have an algebra, sigma algebra on it, on which you can define probability measure. The probability is the mapping of the combination of nearly every possible combination of the possible elementary events to the real numbers in a way that the probability is always non-negative. The complete omega has a probability 1, and as well for countable disjoint events, the probability of their union is equal to the sum of their probabilities. So this is sufficient to define a consistent definition of consistent notion of probability. Let's just some simple definitions to illustrate some simpler notions of intersection, union, and the complementary. So from these axioms, you can derive some straightforward consequences, like, for example, the probability of a set and plus the probability of its complementary. The set is here, complementary is here, is equals to 1 because the two events make up together the whole collection of possible elementary events. Another consequence is that the probability of the union of this whole thing is equal to the probability of each of the elements, but you have to remove the intersection, the probability of intersection, because you counted it twice. And another interesting things that again Bayesian statistics is based on the conditional probabilities. Sorry.
Oh, I said bless you. Sorry, I didn't mean to interrupt. Sorry.
Okay. So conditional probability. It's the conditional the event A, the probability of event A conditioned on B is just the probability of the intersection divided by the probability of the conditioning event. Also, based on this, you can give another important thing, the law of the total probability, that the probability of any event here in the middle can be decomposed according to the probability, according to its conditional probabilities on a set of disjoint events. Disjoint is very important. I have already seen this, that these events should be disjoint. It's very important. I have recently seen a paper where they applied this thing on not disjoint events, and they have to find some very twisted arguments to do what they wanted to do. So it was a little bit flawed. Finally, they arrived to something useful, but it was just could be just reasoned by some common sense. You find a better model, quite a better performing model to do the best. That's even when you want to combine models, non-exclusive models, then you can weight them according to their usefulness. But they are not exclusive, so you cannot argue with the law of total probability. Okay, so that's all for that was just a reminder of probabilities, and now we'll go to random variables and their distributions. The random variable is defined as an outcome of an experiment with a probability for each outcome. So at the background you have a space of events with the possible combined events as the algebra of events, and you have a probability for each outcome. Your experiment can be just tossing a dice, for example. There are basically we deal with two different we use two different kinds of them. One for which we have a density, probability density, this little p here. Here, this is the probability density of a normal mixture. You can define probabilities of events A on any space of it, like here in the real line. The event A is that the outcome is smaller than 0, and it's just an integral of the probability density. Now, this is quite restrictive. There are probability laws for which you don't have density. Right now we forget about them because we don't. Most of the probabilities that we deal with in every day have a density. The other type is the discrete density. Discrete laws for which you have a certain countable set of possible outcomes. Like here, this is a Poisson distribution. Again, you can give combine the probability of the combined events by just summing up the outcomes that are corresponding to your event. It's just created by sums. The important thing that a density is always non-negative, and it integrates to 1 if you integrate it all over the space. This corresponds to the first axiom of Kolmogorov. And for the discrete densities, you also have the non-negativity criterion, and that it integrates up to it sums up to 1. For the continuous distributions, a single value on the real line has no probability. This should not be forgotten. On the other hand, the density could be intuitively regarded as the probability of a very of the event of B falling in some very small interval around the density, the x. We can define also multivariate probabilities. The probability, again, it's just an extension of the univariate definition. Probabilities are defined by a multivariate integral over the multivariate density. And again, the density will give the probability of a point, an observed point around x and y. This is just a two-dimensional example. For multivariate probabilities, we can define the marginal density, which is just the integral of the probability density according to every other variable, and then you obtain the marginal density on the others. In higher dimensions than 2, you can find the joint marginal of 2 variables if you integrate out the 5 others, and so on. So this simulation just shows 2 independent gamma variables multiplied up. You can also define formally the conditional probability similarly to to the simple probability illustration before 5 minutes ago. It's defined by the division of the joint probability by one of the marginal, by the conditioning one marginal, and you can also define the law of total probability similarly to the probabilistic definition of it. The probability density, conditional probability density times the condition integrated out will give the marginal. And from that base rule follows, if you apply the rules of how to deal with probabilities, then you can arrive to this decomposition. It forms the foundation of the Bayesian approach to inference. And well, an intuitive interpretation of it can be given by if you condition, for example, y on y being a certain value, and you are curious about the density of the other variable, then you can imagine that it's just you fix the value of y in the probability density. So these are just the conditional probabilities in my independent gamma model. You can define also, you can characterize these distributions with many things. For example, you can define the expected value. That's the first order moment of the distribution. It's something like the mass center of a mass distribution along, for example, a line. This is the point. The mean is the point where you should put a support under it. And then it's in balance. So that's the mean. You can also find the expected value of any function of your variable. That's the definition. Here it is. You can define the variance. This is something that characterizes the span of the distribution, how scattered, how stretched in the space. The definition goes like this, and you can also define the higher order moments, just taking the expected value according to this definition of the powers of it, and you can centralize also. So these are very important. You can also compute, for example, the skewness, which is equivalent to R equals 3. R equals and then this measures the asymmetry of the distribution. The fourth moment is also used when R equals 4. This is somehow the boxiness, how concentrated the distribution is in the middle, and how heavy the tails are. That if that's smooth and low, like a normal distribution, the kurtosis is small. When it's very concentrated and very flat and slowly decaying tails, it's a higher number. Covariance and correlation. When you have more than one variable, you can define their covariance just with the generalization of the variance. It's the expected value of the deviation of x times the expected value of the deviation of the mean from y. Sorry, this should be a y. I made an error here. It's a y. And the correlation is just the covariance matrix, just the covariance divided by the variance of the square root of the variance of x and the square root of the variance of y. And here, this is the well-known illustration of the correlation. That the correlation measures actually not dependence, but indeed linear dependence. So as long as the two variables are linearly correlated, it will give a non-zero value. But there are also many configurations, symmetric configurations, where this quantity will give you 0, and even so there is dependence between the two. So what is essential? Non-zero covariance, non-zero correlation means that there is dependence. There is some linear dependence, at least in your data. But the converse is not true. If the correlation is 0, nevertheless you can have any sort of dependence apart from linear. The linear part is measured by the correlation. Otherwise, not anything. Monotonic dependence types between x and y can be measured by rank correlations. This is called the Poisson correlation. I wrote here. You can do the same thing on their ranks, and that would be the Spearman correlation. And there are other kinds of measures. Those are better in detecting nonlinear relationship as long as they are monotonic. Okay, I just tried to collect some important distribution. This is really like a long list of not very exciting things. The first important distribution that I mentioned is the Poisson distribution. This is, for example, for photon counts at the faint end, any sort of counting data, like for example in space, the number of certain types of objects on the sky and other things like that can be described with the Poisson process, not necessarily homogeneous, but the variables that you observe in a little slice of the space can be modeled as Poisson. Binomial distribution occurs when there is a two-valued variable, and the two value can be taken. Two values can be observed with different probabilities, and there is no other event. Probability is again discrete, of course, because you have just integer numbers to be observed. You try n times, and how many success you have out of this n times. That's a binomial variable. Now let's go to the most important, continuous density. It's the Gaussian. The definition is given there, hopefully, all right. That's what is used the most frequently, I think, everywhere in the world. The standard normal variables are defined by the zero mean, and the standard deviation equals to 1. That's very important because statisticians like to give their convergence theorems, limiting theorems, asymptotics in terms of standard normal variables. It might be useful, and we will use in the exercises that it is linear, so that if you have a normal variable, with whatever mean and whatever standard deviation, if you multiply it with a scalar and add a scalar, so that you shift it and you change the scatter of it, the resulting variable will be again a normal variable, and it will have the mean, sum of the original mean plus your shift, and the variance, not the standard deviation, but the variance, which is the square of it, will be the sum of the variances of the two. In other ways, that's also important because it's the maximum entropy distribution of all the continuous distributions. And what else? For now, I think it's enough. Also, with the linearity, there comes a nice bonus that you can standardize variables just by removing their mean and dividing by the variance. which is very useful when you have a heteroscedastic data set and you want to do distributional checks. Then you just remove the mean of each variable, as unexpected, and divide it by the standard deviation. And then you are okay. Every variable is on the same scale, and you can make any sort of diagnostics, transformation, and so on. It's helpful sometimes also in simulations. Okay, one important derived distribution. This is the sum of squares of independent standard normal variables. It's so important that in astronomy the least square regression is sometimes called the chi-square method. Indeed, the sum of squares there is related to the chi-square. As it shows, if you sum up if you just square one normal variable, you get the black distribution. If you sum two of them, then it's still a monotone distribution starting with 0. When you have a higher degree of freedom, you sum up higher number of square normal variables. You get distribution which starts at 0 and have a mode somewhere. Mode is not anymore at 0. And yeah, so because of the mean is equal to the degrees of freedom for every single distribution, if you divide the sum of squares from your model with the degrees of freedom of the model, then you should get something close to 0, at least in the mean. The distribution will not be the same for every mu, but at least the mean should be close to 0, to 1. Sorry. Important distributions also, it's the T distribution. It comes up very often when you have normal variables and you divide them with an estimate. You try to scale them, to standardize them with an estimated variance that you did not know, estimated standard deviation. This, the fact that the standard deviation is estimated in this case, it increases the variability of the scaled variable, so it's not anymore normal, but something that has a heavier tail. Again, it comes up as the distribution in linear regression when the variance is unknown and you have to estimate it. When the degrees of freedom is 1, that's the Cauchy. That is called Lorentzian in astronomy. It has extremely heavy tails, such heavy tails that you cannot define the mean or the variance of it. They are infinite. So this distribution is something that should be treated with caution. You don't use as an estimate. If you have a suspicion that your distribution is so very heavy tailed, you don't use the mean and the empirical mean and the empirical variance as estimators of the center and the scatter of it. It's simply divergent. On the other hand, you can use the median. Multivariate normal, again, a central importance in classical statistics and also in Bayesian statistics, because that's the basics for many much more involved models when you introduce dependencies in the mean and in the variance of it. And also in classical statistics, this is this serves limiting distributions to many estimators, including the maximum likelihood. So that's an important thing. It's completely characterized by its mean, and the variance covariance matrix, you can specify it independently of each other, and then it's sufficient so that you don't need to give any higher order moments or other variables. Yeah, and the correlation again, so this is the sigma is the covariance matrix. From the covariance matrix, you can again define a correlation matrix for any element for any two variables in the multivariate distribution. Okay, so that's not all. Statisticians defined all sorts of other models that you can consider if you have certain types of data. It depends also always on the type of the data that you have. Like for example, if you have random variables obtained in linear models and you want to do some comparison, some model comparison of two multivariate linear regression, which is the best nested, then you can use this one. Exponential, when you have events like arrival times of photons and things like that, which come from a Poisson process, you can use the exponential after this as the distribution of the times between times. Also, the exponential distribution is used to model lifetimes. I don't know about it in astronomy. I know about biostatistical applications. Gamma is used the same way, survival time. I personally used it also to generate random error bars for models where you have heteroscedastic models. The Laplace or double exponential model is the exponential is something like starting from zero. It's given only for positive variables, and then exponential decays. The double exponential is just taking it both sides. So you put an absolute value in the variable. This serves prior for the lasso regression. It's a certain way of penalizing a regression model. If you have too many variables in the regression model and too few observations, then you have too mathematical trouble. You cannot fit with too few observations, too big models, because simply it's over defined mathematically. In this case, such things can help. You put penalization to obtain too big coefficients, and then you with that the likelihood is higher for models that contain very large coefficients in very large numbers. This will drive down the number of coefficients. You will get a significant estimation of only those that are big, so that you estimate only the big and supposedly important variables in your model, and just the others are dropped, and then the model becomes otherwise it's very useful if you think that in your high dimensional model there is only a few coefficients that are very important. The uniform distribution, again, it's quite important. Probabilities can be generated from the uniform distribution, and then if you want to simulate from a not very nice distribution, which is directly would be very hard, but you can apply, you can compute the value of this distribution, of this cumulative distribution function at any point quite easily. Then you generate normal variables and take the value of the cumulative distribution function at this basis, and the resulting obtained variables will follow the distribution from which you wanted to simulate. So this is the probability integral transform that I try to explain. Log normal, this is these are variables that for which the logarithm is normal, so it gives you a sort of multiplicative central limit theorem. I will mention the central limit theorem later. Extreme value distributions, it's not very well known in astronomy yet, but they are very useful. They are valid distributions for maxima of long blocks of observation. If you want to examine the process only at very high levels, then this is a good idea. Similarly, for the generalized Pareto distribution, in this case, you just put a high threshold and take every observation above this level, and they will approximately follow a generalized Pareto distribution. With both, the nice thing is that this works contrary to the central limit theorem. This works also on dependent data. Not every type of dependent data, but many types of dependent data it works. And just to mention a multivariate example, prior of the conjugate prior on the covariance matrix of a normal distribution, and many others like this. So it's quite nice. These are just univariate distributions. You see here the central position normal, then non-central chi-squared. So you can follow the base. Even the code is given how they depend on each other. And again, I must mention that this is not a complete version, and the multivariate is completely missing from them. Okay, so this is the map on which we would like to find our way. I would like to remind you that the whole point of this thing is that the likelihood, whatever you do with your data, is of central importance. It's if you pick it badly, no good prior could be put that could be informative, that could give you the right answer if the model is misspecified. So try to find the model. Okay, so let's see some techniques what to do. Here is a simulated data, and here is what usually is seen in the papers, a histogram, and overplotted an approximate normal distribution. So is it normal or not? What would you say? Yes? No reply. Okay, so this is a normal distribution, but you don't see it. You are right if you do not want to answer me. So you don't see. Statisticians prefer the one-type plot, which is a very useful tool I found. This consists of, well, first of all, you sort your data in increasing order. That's what is symbolized by this parenthesis around the index. So it's sorted. And also, you take the inverse of the normal distribution, so that the values of on the real line at which the normal distribution takes the probabilities, the integral of the normal distribution, so that the cumulative distribution function of the normal distribution takes the probabilities g over n+1. So it's sort of trying to compare our values, observed values, to something that would be observed in a perfect world from a perfect normal distribution. So now I would like to go to the exercises, to open it and see and do the first exercise. It's very simple. I will not do it here on the screen, I think. is the very first one.
Mitzi, can we pull up the notebook on your computer? Oh, I was saying, can you pull the notebook up here so everyone can just see it?
The exercise. In the ideal case, you should see something like this. Got it? Okay, so let's go back to the. So it looks something like this if I apply my QQ plot on this data set. You have to see 9 of these things on your screen, and it seems that everybody got it, and it was quite line-like in every case. Now, again, please go to the exercise tool. Go there again.
So your main point there is binning destroyed information.
Exactly.
Yeah.
That's
So
the
it's not the
conclusion.
fact you're using quartile, that's a way to avoid binning. So
Yes.
any cumulative plot would show the same
Yes.
information.
Binning and the binning, the loss of information caused by the binning can be catastrophic in the tails. And tails can be catastrophic for estimation. So if you have a heavy tail distribution and you cannot see it, then you might have a very flawed and very biased. Just similarly to skewed distributions, it's very hard to see on the histograms, is it really significantly skewed or not? Skewed distributions instead of normality, again, can introduce a strong bias in the estimation. That
But you introduced two different things. One was using a cumulative distribution. The other was normalizing it to a straight line by using the inverse Gaussian. So you could have, so you did two clever things at once, right? You hid them inside one exercise.
Yes, that's the second thing. And so I ask you now to do the second exercise. I would like just to make you see how stable are the QQ plots. So for 4 observations, you cannot do a histogram. That's completely stupid. Would be completely stupid. Here, with the QQ plots, at least some partial idea can be derived if it's very, very strongly different from what I expect for a normal distribution. Then you can be already warned a little bit that I might be on the lookout for other effects when I will have new data points. It's even it's still variable when you go to a little bit higher numbers, 20 observations on the second figure, and with the 200 it's already quite nicely lined up. And as well, I said that the normal distribution is linear, so you can estimate even if you plot against the standard normal quantize as we do it here, you can put put a line. You can estimate the standard the parameters of the normal distribution by the slope of the line and the intercept of the line. So that will be the one of the estimations. In any case, if you have other distributions, very rough first estimate of the rotation and the scale parameter of these distributions can be given by the slope and the intercept of these lines. So that's a very useful animal. That's this group. Okay, so that's it. Could you do it, or shall we wait a little bit more?
Awesome, thank you. Can I do something? Can you make the font a little bigger? Hey everyone, so some of you caught on to this, but one thing you can do in the notebook, which I think makes it a little bit easier to see figures, is if you add percent sign and then do matplotlib inline, okay, instead of popping out this second window, whoops, I didn't mean to do that.
Adam?
Yes?
Also in the general Slack channel, I think Joaquim gave us some handy things for making the plots inline and bigger.
Oh, okay. Well, so you can check the Slack channel, but if you add that line, then the plots will be rendered in the notebook itself, which might make them a little easier to read.
So I guess everybody finished it, and we can continue. So this is a way to see whether your sample is close enough to normal. If it's close enough to normal, then it should be line-like. Now let's take another sample and look at the histogram, classical histogram of it. Again, you cannot really say with this binning whether it's normal or not. You can change the binning, you can shift it, but nevertheless the information will be, as Robert said, lost indeed. Instead, if you want to do a QQ plot, you observe something like this, which is interesting and informative, because you see systematic discrepancies between the line and the dots in the tails. So it seems that the sample values at the negative tails are more negative, systematically more negative than what you should observe from a normal distribution, and then in the positive tail they are bigger. So it seems that the distribution is a heavier tail distribution than the normal distribution, even though on the histogram you don't see anything. So this such a picture can warn you about that you should pay attention to these things, both because you have to discover the reasons why it is. There might be some systematic effect in your data that causes this, or and of course it has a consequence if you want to use some Gaussian likelihood to make your model. Maybe you are better to choose something. Now you can do quantile plots, not just with normal quantiles. I think in this case you can do that in Python by taking probability points from the distribution or for whatever distribution is implemented in Python, and use just simple plotting to do the same thing. You see that if I take a T distribution with the degrees of freedom 8, you get pretty much a line-like thing, and this was the truth. So that was my simulation here. So it seems that the QQ plot is much adapted to discover systematic distribution and discrepancies, which is seems to be important for me and important consequence for me. You read a lot in papers that this and this value is a detection at 3 sigma level, but you never see a convincing argument that this is really normal. So you don't know exactly what this means. A 3 sigma detection has a meaning only when you have a normal distribution in the background. So whenever you want to say this, then please make sure that your distribution is indeed a normal distribution, because in that case you say something. Otherwise, it does not mean anything. If the distribution is standard, is indeed normal, a 3 sigma detection means that the probability that without the effect you could observe this is 0.0027. But if the distribution is a T8 that you see that was by the histogram, it was practically indistinguishable from the normal distribution, this beautiful significance drops to something that is much less convincing. Okay, it's significant, but I would be careful. And especially if you have, if you see the QQ plot and see the systematic discrepancies in the tails, then you can have doubts that there is some systematic effect in the background. You should discover that what it is, what distorts your distribution. Let's see. Okay, so I would like to go and do the third exercise, which is how to see different distributions in this with these QQ plot techniques. And well, I have some propositions in the exercises.
So I'll just chime in. This is a first Tuesday of the month test. This is nothing to actually be worried about happening outside right now.
I thought it's because somebody had made a Gaussian assumption about it.
Okay, so here it is on the screen. I proposed to do that for a Poisson distribution also, just to see how what a discrete distribution looks like with this QQ plot. You can do QQ plot with the discrete distributions also, and otherwise for the parameters of other distributions like the beta and t-distribution and chi-squared and exponential, you go to the documentation of the SciPy for the parameters of these distributions, how to give them. What happens here? First, I define a grid, X grid, on which I can compute the distribution, the density values. This number here. This number here are the probability values, so it's a very low. I would like to plot the Cauchy distribution from a very low quantile to a very high quantile. Then generate 400 points of it, and well, I plot the histogram, and I plot the overplot the density, and plot the q-plot also. So try to do this. If you want, if you are very fluent in Python, then you could use the pattern of doing 9 times as we did it before, and you see how variable what information in fact is in it.
Yeah, she said.
otherwise you don't get it. Okay, so maybe time was enough to explore a little bit what can be the possibilities. Just to recap it, what you had to see when you simulated the Poisson distribution with a low mean. What you assume that there are only a few values, there are horizontal lines on the QQ plot. This is also, of course, indicative of discrete values, the number of points in one line. It gives information which distribution it is Poisson. If you did that with the high mean, large mean Poisson distribution, you saw something similar to the normal distribution. It was almost normal. And this is a manifestation of the fact that Poisson distributions with high mean can be approximated quite well with the normal distribution, and this is why fluxes also can be distributed when they are high. You can take that distribution as a normal distribution. When you simulated the beta distribution, you had something like this. This is a curious beta with one parameter high, relatively high, b equals 2, the other is 0.1. The beta distribution is something that remains always between 0 and 1. And so you see the specific distortion corresponding to this on the QQ plot. The low numbers that are very frequent with this parameter selection is flat. So you see that it does not go below 0. With this parameter setting, you don't really see here. With different parameter settings, you can find similar leveling out at high values. What else? So you already know what is the effect of high tails, heavy tails. It's systematic discrepancy between more negative, more positive, high values, and so on. So this QQ plot also can be used for detection of problems with your data, because until now these are still we spoke only about I wanted to here, I don't know why here, but I wanted to mention the central limit theorem. I should have mentioned it before, a little bit before this exploration, because it is what makes the normal distribution so central. So the central limit theorem says that if you have independent, identically distributed random variables, independence is important, and identically distributed is also important, but you don't have to specify that they should be individually normally distributed. You should require only that their expected value and variance is finite, so you don't apply it for Cauchy distribution or for Lorentzian, and a few others that are less well known. Then the sum of it, the average of it will follow approximately a normal distribution. If you standardize it, like with Sn here, then this follows a standard normal distribution. If you just sum it, you take the mean also follows a normal distribution, and the sum also follows a normal distribution. These are all equivalent presentations of the central limit theorem. So this is why the normal distribution is important. Okay, illustration, again, let's put histograms. So I generated Poisson variables, first 3 of them, then 10 of them, and 100 of them, and added and computed the mean of these 3 Poisson variables, these 10 Poisson variables, and 100 Poisson variables, and I repeated it, I think 10,000 times, and I get a distribution function, something like this. So when you add only a few number of variables, it's very poor, around 10. It's still you can still see the discrepancy of it. The long tail is missing, and with 100, it's already a pretty good approximation. The variance of it, of course, is given by here, the approximate variance. Okay, so I don't know what you think about taking a break, or I think logically this would be the place to take a break, and then we continue with estimation. So until now it was diagnostic, recognizing qualitatively the distributions, then with the so let's take a break. How long should we, Adam?
15
minutes.
We have a 30-minute break on the schedule, so